the next thing that I want to discuss is Schottky's theorem, okay, which is now very easy to prove, okay. So let me write it down. Schottky's theorem. So this is let alpha be a positive constant and beta be a fraction, and a positive real number between 0 and 1, okay. Then there is a constant C alpha beta such that if script f is a family of analytic functions, on the open unit disk, that omits the values 0 and 1 and satisfies f of 0 is bounded above by alpha for all functions small f in the family f, then mod f z is less than C alpha beta for all z with mod z less than beta, okay. This is Schottky's theorem. And the point is that this constant C alpha beta, it depends only on alpha and beta, and it does not have anything to do with what the family is. It works for any family. And such theorems, when they were first proved, they were considered pretty difficult. But then because we have Montel's theorem on normality and Montel's test for normality, it is easy to reduce this theorem, okay. So let me tell you the proof. See, you can see immediately that you want the family to be arbitrary, therefore you consider the biggest possible family, namely you take all analytic functions on the unit disk, okay, satisfying the condition that the value at 0 is bounded by alpha, okay. So you apply it to the largest possible family that you can think of, okay. And see, the moment you are given that these functions omit the values 0 and 1, okay, it means that the family is normal. See, in fact, you see what is Montel's theorem on normality, otherwise called the fundamental normality test. See, if you want to decide a family of meromorphic functions on a domain is normal, then you need to know that it omits 3 values, but 3 values in the extended complex plane, so one of them could be infinity, right. But then if you are working only with analytic functions, you already know infinity is not going to be taken, okay. So you have to only ensure that for a family to be normal, to be able to apply the normality test, you have to only ensure that the family every function in the family does not take 2 values. So here it is given that all these functions, they do not take the values 0 and 1. So if you apply the fundamental normality test, that is Montel's theorem, it will follow that if you take the family of all analytic functions, if you take the family of all analytic functions on the unit disk which omit the values 0 and 1, that will be normal. Okay. So, this is Montel's theorem on normality, right. But then we also saw another theorem of Montel, okay, which was a translation or an improvement of the Arzela-Ascoli theorem, which said that for a family of analytic functions to be normal on a domain, you need that the family is normally uniformly bounded, that is, it is uniformly bounded on compact subsets. So, if you see mod z less than, so let me write, let me consider mod z less than or equal to beta, okay. If you look at mod z less than or equal to beta, so I will change this here to mod z less than or equal to beta, which is what I meant to write but I did not. But if you take mod z less than or equal to beta, that is a compact subset of the unit disk, okay, because it is closed and bounded, and therefore by the other Montel theorem, which is an improved version of the Arzela-Ascoli theorem, the normality of the family will tell you that the family is going to be normally uniformly bounded. So, it is uniformly bounded on any compact subset. So, on this compact subset it has to, all the functions should have a bound and call that bound as C alpha beta, it is as simple as that, okay. So, what you must remember is that we have applied two Montel theorems. One Montel theorem which is which equates the normality of a family, that is a normal sequential compactness of a family with the uniform boundedness of the uniform boundedness of the original functions in the family on compact subsets, normal uniform boundedness, and that is, mind you, that is a improved version of the Arzela-Ascoli theorem, and in fact it used the Arzela-Ascoli theorem plus a diagonalization argument, right. And then we applied the more serious Montel's theorem on normality, the fundamental normality test or fundamental criterion for normality, which is a very deep theorem. Mind you, that was the key to proving Picard's theorem, okay, that the moment a family of meromorphic functions omits 3 values, it is normal. The moment a family of analytic functions omits 2 values, it is normal, okay. So, you apply those two theorems, then Schottky's theorem is a simple corollary, alright. So, it happens that there is a paper of Zalcman in the Bulletin of the American Mathematical Society where several where he explains how several problems in function theory have easy solutions by use of the Zalcman lemma. So, in fact, there is what is called the there is a very deep theorem called Bloch's theorem, okay, and it involves roughly it is trying to estimate the size of the largest size of a disk under the image of a univalent or one-to-one analytic function. You take a one-to-one analytic function, okay, and then you try to estimate, you take the image and then you try to see what is the largest disk, radius of the largest disk that is contained in the image, okay. There are theorems of this type, and there is a particular theorem called Bloch's theorem which is very, very deep, okay, and this can be proved by using the so-called Bloch-Zalcman principle, which is also called as Bloch's principle, okay, and the whole point is Zalcman's lemma is very powerful. It gives you proofs of easy proofs of very deep results, right. So, it's not a surprise that you get Schottky's theorem, okay, as a simple corollary. So, let me write down proof is uses, so let us consider the family of all analytic functions on the open unit disk that omit 0 and 1, this is normal. This is normal by Montel's theorem on normality, otherwise called the fundamental normality test. Or sometimes it is also called fundamental normality criterion. Again, by another theorem of Montel, along the lines of Ursula Ascoli, the family is normally uniformly bounded, hence bounded uniformly by C alpha beta on mod z less than or equal to beta. Okay. See, the point is I did not even use the fact that the functions at the origin are bounded by alpha. Okay. I know that there is a uniform bound, all right, and I simply call that uniform bound C alpha beta. Actually, I needn't put that alpha there, but I can call it C alpha beta. The point is that I have to put in beta because I am looking at the bound on mod z less than or equal to beta, which is a subdisk of the unit disk, closed subdisk of the open unit disk. Okay, fine. So what you must understand that is that this easy proof is because you have the strong Montel theorem on normality, which is a fundamental normality test. Okay, so see, all right. So this is one thing. Then I would like to discuss the solution to the first assignment that I gave. Okay, so here is a problem that I gave earlier. Let D be a domain in the complex plane and f from D to C be continuous such that for some in positive integer n integer f power n is analytic. Okay. Then f is analytic. Of course, you know, I need to take n greater than 1 because otherwise it is trivial. Okay, because if I put n equal to 1, f power n is just f power n is just f power 1, which is f. Okay, and what is the solution to this? Well, so the first thing is that so f power n, first of all, f power n means f of z whole power n, which means f of z into f of z multiplied n times. Okay. The first thing I want to tell you is that we will use the fact that the zeros of an analytic function are isolated. So since f power n is analytic, okay, the zeros of f power n are isolated, but then the zeros of f power n are the same as the zeros of f. Therefore, the zeros of f are isolated, okay. And therefore, what we will do is we will first throw away the zeros and look at the complement of zeros in the domain, which is a subdomain, okay, all right. And what we will do is that on that subdomain we will first prove that f is analytic, all right. And then we will have to worry only about these points where f becomes 0, all right. But then we can apply Riemann's removable singularity theorem, because each of these points will be isolated points in a neighbourhood of which f is continuous. Therefore, they will be analytic even at those points, and that is the proof, okay. So, so let me write this down. Since the zeros of an analytic function are isolated, the zeros Ez of f power n, the set of zeros is isolated, but the set of zeros of f power n is the same as the set of zeros of f. So, the set of zeros of f in D is isolated. Of course, you know, when you want to say the zeros of an analytic function are isolated, you must make sure that the analytic function is not identically you know, constant. So, this the only case where this will fail is when the analytic function is identically 0. If the analytic function is identically 0, then the 0 set is the whole domain, alright. That is the only extreme case. But of course, if f power n is identically, if f is 0, then f power n is identically 0, and if f power n is identically 0, f is 0. So, let us assume that f power n is not 0, assume that f is not 0, okay. So, there is nothing to prove if f or f power n is identically 0, okay. So, that has to be, we assume that f is not identically 0 on D, right. So, that is the only thing that we will have to worry about. When you want to, whenever you want to apply this result that the zeros of an analytic function are isolated, you better make sure that the function is not identically 0, okay, and usually we are not interested in that function, right. Fine. So, so now what you do is, in any case, you look at, consider D minus ZF, okay, throw away the zeros of f, okay, it is an isolated set of points. So, you get a domain again. So, D minus ZF is also a domain, right, and it will still be open, okay, it will still be an open set, and because you are throwing away some isolated subset and it will also be, it cannot get disconnected, okay. So, because you are just throwing isolated points away, it cannot get disconnected. So, D minus ZF is also it is also a domain, okay. And now we are going to look at this domain. The advantage with this domain is that f power n does not vanish, f does not vanish because the zeros have been thrown away. So, f power n does not vanish, and f power n is an analytic function, okay. So, you have a non-vanishing analytic function on a domain. Now, you know, if you take any point in the domain, if you take then there is a sufficiently small disk around that point which is in that domain, okay, and the point is that if you have a non-vanishing analytic function on a simply connected region, on a simply connected domain, then you can find an analytic branch of the logarithm of that function, and in particular you can find nth roots of that function for any n. And the point is you can find nth roots which are analytic, that is the whole point. So, if you want to find an nth root of a function which is analytic, okay, then the function should not vanish and the region and the set on which you want to find it must be simply connected, alright. So, the point is that if you take f power n, which is analytic, and f power n does not vanish on d minus zf. So, if you take any point in d minus zf and you take a small disk surrounding that point, in that small disk I can find an nth root of f power n, and what do you expect it to be? It has to be f, okay. But this nth root is supposed to be analytic, therefore it will prove that f is analytic, okay. So, but a little bit more has to be written down, okay. So, let us do that. F power n is analytic and non-zero on d minus zf for z naught in d minus zf. There exists a small disk, small open disk mod z minus z naught lesser than epsilon in d minus zf. Since this is simply connected, and f power n does not vanish, there exists an analytic branch of log f power n in mod z minus z naught less than epsilon, okay. Consider the analytic function. So, let me call this analytic branch as g, okay. Consider the analytic function e power 1 by n g, okay, which is actually, see, it is e power 1 by n, g is actually a log of f power n, okay, and you know this must be f, alright. You should expect this to be equal to f, alright. Now, you see, we will use the following. How will you show that this is the claim is that e power 1 by n g is actually equal to f, okay. The claim is e power 1 by n g is actually equal to f. Once that is proved, it means f is analytic, because e power 1 by n g is already analytic, and e power 1 by n g is analytic because g is analytic. And why is g analytic? Because g is an analytic branch of the logarithm, okay. So, we just have to prove that e power 1 by n g is equal to f in this small disk, okay, and this will show f is analytic in a small disk, but then the point z naught was arbitrary, so it will show that f is analytic on d minus zf, okay. And then at points of zf you can apply Riemann's removable singularity and conclude that f is analytic on the whole of t, alright. So, the only issue is now that I will have to show that e power 1 by n g is f, okay. Now, what is common to e power 1 by n g and f? They are both nth roots of f power n. F is an nth root of f power n by definition, alright, and e power n 1 by n g is also an nth root of f power n, because if I take e power 1 by n g and raise it to the power n, I will get f power n, okay. I will get e power g. If I take e power 1 by n g and raise it to the power of n, I will get e power g, but g is log f power n, so I will get e power log f power n, which is just f power n, okay. So, both e power 1 by n g and f are nth roots of f power n, alright. And the point is, you see, you take if you see the, so now we have to use the following property. If you take any two logarithms of a complex number, okay, they will differ by a constant. They will differ by a constant multiple of 2 pi I. You see, if you calculate the logarithm of a complex number, of course it is only defined for a complex number which is different from 0. There is no logarithm for 0. Okay, so if you take a non-zero complex number and calculate its logarithm, then you know different logarithms. Logarithm is a multi-valued function. Okay, and the point is that the real part is the real logarithm of the modulus of the number, which is non-zero, since the number is non-zero, and the imaginary part is the argument of that number, of that complex number, and the argument can be the argument is defined up to a multiple of 2n pi, up to a multiple of 2n pi. Therefore, the imaginary part of the logarithm can be changed by 2n pi I. I mean by 2n pi. Okay, so any two logarithms of a number will differ by 2n pi I. We have to use that for each z in mod z minus z naught lesser than epsilon. We have to do a little bit of thinking. See, you look at the function f of z times e power minus 1 by n g of z. You look at this function. Okay, see, look at this function. This function, if I raise this to the power of n, I will get 1, because you see, if I raise this power n, f of z will give me f of z power n, and e power minus 1 gz, if I raise it to the power of n, I will get e power minus gz. Okay, but e power minus gz is 1 by f power n, because gz is a log of f power n. Alright, so this is equal to 1. So this means that f of z into e power minus 1 by n g of z is an nth root of unity. Okay, and this nth root of unity, but the point is it's an nth root of unity, and this nth root of unity in principle could change if you change this z. So I'll call it as omega z, because it depends on z seemingly. Okay, for every z, if you take f of z times e power minus 1 by n g of z, its power n is equal to 1. So it is an nth root of unity. So for every point z you are getting an nth root of unity. Call that function as w of z. So w of z is that function. Okay, but you see, what is this? So I am just calling this function as w of z. So what is w of z? W of z is just f of z times e power minus 1 by n g z. Okay, but notice here is where I will use the fact that f is continuous. See, I have been given that f is continuous. So f is continuous, and e power minus 1 by n g z is also continuous. So the product is continuous. So w becomes a continuous function. W or omega of z is a continuous function. So it's a continuous function from a disk. And what is the image set? It's the nth roots of unity. That's a discrete set. Okay, therefore the image has to be constant. Okay, the image of a disk has to be connected under a continuous function. So you must get a connected subset of the set of nth roots of unity. It has to be it can be only a constant. Okay, it can be only a singleton. So that means that this omega of z is a constant. It's one. You get the same nth root of unity for all z. Okay, you get the same nth root of unity for all z. So that is where you are using the continuity of f. Okay, since f is continuous, w is continuous on mod z minus z naught lesser than epsilon, which is connected. So w of z is equal to a constant, nth root of unity. So what you get is, you get f of z is times e power minus 1 by n g of z is equal to constant. So which means which tells you that f of z is equal to the constant times e power 1 by n g of z, but of course the right side is analytic, so f is analytic, so which is analytic on mod z minus z naught lesser than epsilon. Okay. So so the moral of the story is that since z naught was arbitrary, you get that f is analytic on d minus zf. Okay. On d minus z of f. Now I will have to only worry at points of z of f, points at which f becomes 0. You take a point where f is 0, that is of course an isolated point, we have already seen that. So it is an isolated singularity for f, alright, but f is continuous there. Therefore by Riemann's removable singularity, f is analytic at those points as well. Therefore f is analytic on all of t. Okay. So it is an application of Riemann's removable singularity theorem. At each point of ZF, we have an isolated singularity of f, but f is continuous there. So by Riemann's removable singularities theorem, f is analytic. Thus f is analytic in T. Okay. So so that is the proof that f is analytic. Okay. So you should see that the point is that you are bringing in, you are using isolatedness of zeros of an analytic function. Okay. You are using the existence of an analytic branch of logarithm. You are using Riemann's removable singularities theorem. You have a question? No, it's what we have proved is around that point f is analytic, you have proved. So it becomes if around a point a function is analytic, that point is automatically, by definition, it's a singularity, it's an isolated singularity. And Riemann's removable singularities theorem applies. Okay. What is a singular point of a function? It is a point which can be approached by points of where the function is analytic. And what is an isolated singularity? It is a point where in a deleted neighbourhood the function is analytic. So if you take any point of ZF, it is an isolated point, and you can find a deleted neighbourhood of that point where the function is analytic, because we have already shown that the function is analytic outside the zeros of f. So that point becomes an isolated singularity, and then the question is, what kind of isolated singularity is it? And you know, Riemann's removable singularity theorem says that if the function has a limit at that point, or is continuous at that point, or is bounded in a deleted neighbourhood of that point, all these things are equivalent to the function being analytic at that point. You can extend the function to that point, you can redefine the function value at that point if it is not already defined, and make it analytic. But in our case, the function value at the points of ZF is 0 by our own definition. Okay, and the point is, again, it's given, you are again using importantly the hypothesis that the function is continuous even at points of ZF. That's the importantly used. You're given the function is continuous everywhere. So in particular, the function is continuous at each point of ZF, and you now apply Riemann's removable singularities theorem. Okay, that's one thing. And then of course I also wanted to discuss this problem, namely that the only onto maps from the complex plane to the complex plane are of the form z going to a z plus b, where a is not 0. Okay, so these are the only automorphisms of the complex plane. Okay, so let me do that also, because it's an application of the idea of singularities. So here is another problem. The only bijective the only bijective holomorphic maps f from C to C are those of the form f of z is equal to a z plus b, where a and b are complex numbers and a is not 0. And what is the solution to this? Well, the point is that if f from C to C is bijective, then f inverse from C to C is defined and bijective. Okay, and mind you that see f is f is analytic, and there is the inverse function theorem which will tell you that f inverse will also be analytic, because f inverse will be locally analytic. Okay, so by the inverse function theorem, f inverse is analytic. Okay, and now we use the following thing. You treat infinity, so the whole point is to treat infinity as an isolated singularity of f. Okay, you treat infinity as an isolated singularity of f inverse. Okay, so you look at f inverse, okay, and look at infinity. All right, infinity is an isolated singularity. Okay, and or you can also take f, it really doesn't matter. Now what kind of singularity is isolated singularity is infinity. It can be either removable, or it can be pole, or it can be essential. Okay, if it is removable, since f is entire, it will, by Liouville's theorem, f will become a constant. Okay, so certainly f is not a constant function because it is bijective. Okay, it's surjective. So so infinity is not a removable singularity. The other possibility is infinity is a pole. If infinity is a pole, then f has to be a polynomial. Okay, but if it has to be bijective, in particular if it has to be injective, it should be a polynomial of degree 1. So it has to be of the form a z plus b. All right, and the only other possibility is that f is the infinity is an isolated essential singularity. But if infinity is an isolated essential singularity, then in every neighbourhood of infinity, f will take every complex value except 1 several times, in fact infinitely many times, and that will contradict the injectivity of f. So it cannot be an essential singularity. So here you're using Picard's theorem. All right. So the moral of the story is that because of Picard's theorem, you are forced to conclude that f is of the form f of z is of the form a z plus b. All right, and a cannot be 0. Okay, so this is an application of Picard's theorem. That's why I wanted to mention it. Look at z equal to infinity as an isolated singularity of f or f inverse. It can't be removable by Liouville. it can't be essential by Picard. So, it has to be a pole, hence a polynomial. This must be of degree 1 by injectivity, and that finishes the proof. Okay. So, I will stop here.